Great. Okay, very good. Well, look, Christine gave a wonderful overview of how and why we want to use advanced simulation for earthquakes. And I too live in California, and I live in the Northern Bay Area, and I work at Berkeley Lab, which is literally 200 yards from the Hayward Fault, which is about 10 years on average overdue for a big earthquake. So we care about this topic personally. I really want to focus a little more in my talk on the computational aspects of what you just heard. And in particular, the implications for exascale computing as we move forward in this domain. And the project I'm going to talk about is a cooperative project between Berkeley Lab, Lawrence Livermore National Laboratory, and the University of California. And it is funded as one of the application development projects in exascale computing. And so as a longtime lab geek, I grew up most of my career at Lawrence Livermore National Laboratory. I really wanted to do a shout out to this nation's advancements in high performance computing. I think it has been remarkable. And if you look at this particular slide, it goes all the way back to the 1950s with the UNIVAC starting at Livermore. And what I would point out is that that curve of performance is absolutely up and to the right everywhere. And so if you think about the evolution, we started out with mainframe era computers. When I hit at Livermore in the early 80s, we were still using CDC 7600s for some of our calculations. Then we moved into the era of vector machines with Cray, the Cray 1s and the YMPs, which was wonderful. And then, you know, post 1992, a defining event when the nation had a cessation of underground nuclear testing, and they started the ASCII program to really allow stockpile stewardship with a far more advanced computational capability. That really drove the era, in my mind, of distributed high-performance computing. And so if you look at that, you go through these different epochs there always seems to be a new idea that keeps that code going up and to the right and doesn't allow it to plateau. And I really think the promise of exascale, as you see when we're now here in 2017, is can we keep that curve going in a very meaningful way? So it's an exciting time from that standpoint. So you may know, I'm sure a number of you know, the objectives of the DOE Exascale Computing Program. I would parse those into three: advanced hardware development, new platforms. A lot of those are under NDA, so we still don't know a lot about those. They will be emerging. You probably saw last week the DOE committed $1.8 billion for those new platforms, so that's exciting. The DOE Exascale program had a call for applications for exploiting exascale computing and getting ready to exploit that computing. It was competitively based, and you had to demonstrate a significant need for exascale. You know, it had to be an application where exascale can make an impact. The project you're going to hear about today was one of those, and it has to do with seismic simulation. And then finally, software technology development. As you think about these big machines and ever bigger problems, just the management of data, as we heard a minute ago, is really a challenge. And so Exascale is addressing all three of those areas. And really in cartoon fashion from the program, we are trying to get US high-performance computing onto a different vector, significantly different vector. The pink vector schematically shows where we are now, and we'd like to get up to the blue. So that's really the motivation. So I will also second something, and I think in the last presentation you really saw this, is that it really is a transformational era for earthquake hazard and risk assessments. The traditionalists, beginning with the 1960s, have always looked at the hazard problem empirically because they had to. And so there has been a very large body of knowledge that's built up by looking at past earthquakes from all over the world and homogenizing those in some sense into a probabilistic framework and trying to predict motions that you would observe in a region or a location in the future. And that is really something we've had to rely on. I think people are beginning to recognize that there are shortcomings with that. If you're looking at data from an earthquake in Taiwan and trying to understand those motions, it may or may not have great relevance to an earthquake in the Bay Area. It certainly has some relevance, but maybe not great. And so what people have begun to see, even the advocates of empirically based methods, is that as they get more data, almost anti-intuitively, some of the uncertainties increase rather than decrease. And so it's really a problem. High-performance computing can help solve and address that if it's done appropriately. And I will say, as exciting as this is, the jury is still out on exactly how we're going to use high-performance computing in an engineering sense. And I'll talk a little bit about that as I get to the end, what the options and opportunities are there. So our Exascale Computing Project is really looking at developing a robust computational framework for both hazard and risk. And so in this cartoon, I show, like you heard in the last presentation, we want to have a very high performance code for representing and modeling earthquake ground motions deterministically. And then we want to, in a meaningful way, transfer those motions into structural response. And so what we are actually doing, well, I should mention our team, that's a multidisciplinary problem. You're crossing disciplinary boundaries from the engineering discipline to the seismology discipline and science. And you really need computational scientists and mathematicians if you really want to drive the bleeding edge of this computing. So our team has a little bit of all of that in sort of traditional national laboratory fashion. So I put Anders Petersen and Hans Johansson first. They are applied mathematicians / computer scientists. They are central. All the discipline people you see around the outside know where they want to go and what they want to do. The computational scientists are key to helping us know how to get there and exploit these emerging capabilities. So both in terms of algorithms and machines, they're absolutely essential. Then we have structural mechanics people, and I happen to be a structural mechanics person. We have seismologists at Lawrence Livermore that are operating the codes and doing validation. And then we have geomechanics people from the University of California, so that's our team. Doing this end-to-end simulation, we are relying on software that was developed at both Livermore and at Lawrence Berkeley Lab as our starting point. And I'm going to talk a lot about the SW4 code, which is shown on the upper part of this slide. That is a fourth order finite difference program, both fourth order in time and space, with a lot of advanced algorithms for modeling seismic wave propagation. We are formally linking and coupling that code to codes that we are developing at Lawrence Berkeley Lab under support from DOE for analysis of coupled soil structure systems. And so, for example, if you have a nuclear power plant or some other structure and you want to understand not only the regional variation of risk, as we heard in the last presentation, but what do the incident seismic motions arriving at that site really look like? Because we know they're not vertical, one-dimensional, vertically propagating shear waves as we presumed. We can begin to do that computationally. And so we're going to really couple both geophysics and engineering codes. This is my rendition of the slide that Christine showed in the last presentation. If you look at, and here's the fundamental problem, if you look at the natural frequencies of vibration of man-made structures, they are higher in general than where we can accurately compute to in a seismological standpoint. There is a mismatch. So a lot of these big historical models that have surface topography and attenuation in the whole 9 yards on a large scale, we've traditionally been able to compute to maybe 2 hertz. And so we're been very limited by that. We've been also limited by, as we heard, our geologic understanding of fine scale geology to populate those models. So we have to overcome both those things. This project is trying to develop cutting edge software so that we can remove the computational piece from being a barrier and actually focus on the physics of solving that problem. And so this just shows you, engineers are driving this. Not all seismologists care about simulating at 6 to 8 hertz or 10 hertz. They're suspicious of it, so we're bringing the community along in some sense. So really the computational challenge is 2. Number 1 is to run much bigger models with much higher fidelity and resolving much higher frequency much faster and resolve those frequencies, but they have to be fast. If we can only do a single earthquake realization in a 20 or 24-hour run, that's really not where we want to get to. We want to drive that computational time down so that we can explore parameter space and look at the uncertainties, and so those computations have to be fast. So higher frequency, faster. And then, of course, representation of fine-scale geology. We're incorporating automated algorithms for both waveform inversion, so we can use small, frequently occurring measured earthquakes to constrain the geology, and then as well, overlay stochastic geology in our models so that we can represent some of that very fine-scale geology. Just to make a finer point of these objectives, if you think about historically, and we may have a 12-hour run in one of our big computers at Berkeley, and we may resolve to maybe 2 hertz in the Bay Area. If you look at the waveform of that, it looks like what you see on the left-hand side. If you have a 10 hertz resolution, on the other hand, it looks like something on the right-hand side, where you have much higher frequency that has implications and gross impact on a lot of the structures we care about. So we want to get from the parlor trick of running a very low frequency, very long simulation on the left to running a routine, very large scale simulation on the right. And we want to be able to do that quickly. So I'm going to talk a little bit about what we're doing and about the attributes of the SW4 code, because that's where the big lift is. And so SW4, as I mentioned, is a seismic wave code of fourth order. If you look at a cross-section through the Earth, you have topography, surface topography you have to represent. We don't want to model a flat Earth. We have to capture the ups and downs and the mountains and the valleys, because that scatters the seismic waves significantly. We do that by having a curvilinear grid or curvilinear mesh in the top part of the SW4 domain. As we transition down into depth, we transition to a Cartesian grid where we can take advantages of those more regular grid. We think of pencils in our discretization. So a pencil is simply a slice of the domain going from surface down to depth. And we tend to parse that overall computational domain up to pencils and distribute it to the various nodes of a high-performance computer, as you see here in the case we'll be talking a lot about Corey today. So that's the general schema of how we do that. And the attributes of SW4, you know, when you've got mathematicians involved, they prove everything in terms of the algorithms, which is really good. So they've done a very extensive job of looking at stability and proving things work well. As part of every exascale project, we have to establish what are called key performance parameters so that we can judge. We have to demonstrate very rigorously our performance towards exascale goals. We can't just say that, you know, in 3 years and 4 years, we're going to jump on exascale computers and we're going to go to town. We have to demonstrate our progress, both in terms of new algorithms, new physics, and eventually, as these new platforms come on, how well we are utilizing and efficiently those platforms. So we have, I won't belabor this, but we have developed a large suite of example problems. Some run fast, some run long, so that we can exercise all of the inner loops in SW4 for every advancement in every machine as we progress and leap along. So I'll mention a couple of the things we've done already. Just about a year and a half ago, we ported SW4 from Livermore to LBNL. We've gone through a number of optimization things of that code on the Corey machine. We have worked on the inner loops. We've worked a lot on the compilation. As you know, Corey's a fairly new machine. There was a lot of compilation optimization that had to be done early on. And because of the character of our problem and the fact that Corey has a large number of cores per node, we have, our guys have implemented a sort of hybrid MPI OpenMP approach to the parallelization on that platform, which has helped. So that's one thing we've done. Another very important thing, when we first started this project, SW4 did not have mesh refinement, have uniform grid throughout. And so we've also implemented mesh refinement in both the Cartesian portion of the grid as well as in the curvilinear portion of the grid. And basically that means, because we have a profile and the velocity structure of the Earth changes as you go deeper, you can adjust your grid optimally to reflect that velocity structure profile to be most optimal. So we did that. Turned out that the mesh refinement in the curvilinear portion of the grid was a little challenging, but that's been done, and that's going to give us a big speed up. I'll talk about speed up we've achieved in a few minutes. Secondly, I mentioned the notion of going all the way from ground motion to structural response. We have developed right now a series of Python scripts that take either the surface motions or the near surface motions from SW4 and translate those to our structural analysis codes. So at regional scale, we can first run the earthquake ground motion, then we can see what the distribution of risk resulting from that earthquake to structures looks like. And in this case, I am plotting a 40-story building response and the peak interstory drift, or just the worst relative displacement in that building, pursuant to DOE standards. And you can see green is okay, red is bad. And so for this Hayward Fault earthquake, this is one of our first realizations of trying to understand the risk to structures in the Bay Area. So our operational approach is following. We simulate an earthquake, we select a particular infrastructure, we place that infrastructure at every part of that domain and understand what the distribution of risk looks like for that particular structure. Those are some of the things we've done. In 2017, in Q3, as part of our Exascale project, we did our first, quote, science demonstration run to benchmark the code. And so much like you saw for Southern California, we modeled a big chunk of the Earth in Northern California, and we looked at a number of Hayward Fault rupture scenarios. And so we wanted to establish at that time the performance of the code which we could judge progress against going forward. And so we ran a Bay Area model. We resolved it to about 4 hertz, 87 billion grid points, used 470,000 cores and about 12 hours of wall clock time. And I will show you a plot at the end that in the last 4 or 5 months, we have cut that time in half for running this earthquake and can now do it in about 6 hours, which is tremendous advancement. So we've got a long ways to go. But this was just recently documented in a seismological research letter paper that Artie Rogers was the first author on. So this just shows the Hayward Fault rupturing. Similar to what we talked about in the last presentation, you can begin to understand the complexity of the waves and how they get trapped in sedimentary basins. Unfortunately, I go to work every day right about here, can literally spit and hit the Hayward Fault. So this is always something that we look at and remind ourselves. We've also gone and translated those Hayward Fault rupture scenarios into risk for representative structures. This happens to be the risk that would be associated with a typical 3-story steel frame. Again, red is bad, orange and red are bad, yellow's not so good, and green is okay. And we're beginning to see that we can pick up some of the things we would expect, like directivity effects. In this particular scenario, the fault ruptures from north to south or left to right. And you can see it directs a lot of energy and damages more buildings to the south end of that fault. So you can begin to see these nuances and details. So we heard about validation in the last presentation, which is critically important. And our project is about developing the code and the software to enable higher level calculations, but we still want to look and see if our calculations essentially agree in some sense with observations. And so we have been looking at ground motion prediction equations, and we have been looking at structural response to see if both of those sort of map up with what we would expect from earthquake observations. And we're seeing some promising things. We are looking at the scaling of earthquakes, going from a magnitude 6.5 to a magnitude 7.5. We know that the larger earthquakes tend to be more damaging for tall, long period buildings. Why? Because it contains more long period energy content. So we're looking at both time histories and spectra and taking a look at those and say, do these match what the observations of earthquakes tell us, and do they look right? And so we're seeing some things that really look promising, including the fact that in our simulations there's a lot more long period energy content in the larger events. And I'll just show you, in terms of looking what it does to buildings, we're actually seeing from synthetics and real records some similarity in the damage profiles. And so this is a 40-story building, the peak interstory drift profile in that building for an earthquake. Turns out with these near-field motions, both from landers and the synthetic record, it tends to snap that building at about the 3rd point. You can see the kink and cause a lot of damage about a 1/3 of the way up in that building. So we're seeing that both in synthetic and real records. So that's also encouraging. So we're seeing some good things. So let me talk about establishing a figure of merit. And the onus is on us as a project team to demonstrate that we are making progress in moving the code forward substantially. So we have developed a figure of merit for this code that is the frequency resolved to the 4th. Because if you look at the computational effort, as you increase your frequency of resolution that you're resolving in that Earth model, the computational effort, just through an operations count, goes up as the 4th power of that frequency, which is a terrible curve, very, very steep. And so we have developed a figure of merit, which is frequency resolved to the 4th, divided by the wall clock time of that run, because we'd like that to come down. And then we threw in a factor of 7.6, so that our figure of merit, when we embarked on this exercise, would be 1. So we simply scaled to that. So when we first got on Cori, here is the steepness of that performance curve. Just terrible. It's vertical, right, for a given platform. So this was our first calculation on Cori, where we resolved just under 4 hertz at about 25-hour run. These are our successive optimizations we've gone through. We have jumped to here by optimization of the inner loops in the compiler on Cori. So we're resolving 4 hertz in about 12 hours. And that was the run that I showed you that Artie Rogers had in the paper. And now we just reran a couple of weeks ago with the hybrid MPI, OpenMP, and the mesh refinement in just the Cartesian portion of the grid. And we can run that problem in 6 hours for the Bay Area at 4 hertz. So just in that about a year and a half, we've gone from implementation of the code to jumping to 2 new performance curves. And this summer, In Q3, we redo our Bay Area science demonstration calculation, and we will have full mesh refinement in that. And so I am projecting we are going to get somewhere right up into here on a new performance curve when we use all of Cori. And so we are looking at getting to somewhere certainly to 6 and maybe even up to 8 hertz. 8 hertz is probably a stretch, but this is our target for our performance calculation this year. We are wringing out the optimization and the algorithm improvements here. We are quickly going to get to a point where we're going to have to begin to think about more advanced architectures and more advanced hardware to make up the difference of where we'd like to get to exascale, which is over in this box. We'd like to get ultimately here, which is like a 50 to 100x speed up from our first realization of that code on Cori. And so that is our challenge. So next on our agenda is implementing very fast algorithms for inversion. You heard a little bit about this in the last presentation. I will say parenthetically, more and more data is becoming available. Pacific Gas and Electric is, those of you who live in California, you have a smart meter on your house. There are tens of millions of these, and they are contemplating the feasibility of putting small accelerometers on every single one of those boxes so that we would have an incredibly increased dense data that we could utilize both to calibrate as well as validate these models. That would be exciting. And then we are also, as we move forward, as we exhaust these advanced algorithms for SW4 improvements, we really have to think about the next generation machines and what are we going to wring out of those. And so we are utilizing the software technology development of Exascale, where they're working on special things like C++ libraries to help implement and make seamless the implementation of the code on GPU-based machines. We are going to be able to begin to do things of that ilk, and we've done a little bit of exercise already comparing hand-coded things for GPUs versus Raja libraries, and you don't pay much of a penalty. So that's exciting. So those are the kind of things we're focused on next. So let me get to my slide. How far can this go? You know, these are really, really slick, interesting calculations, but it wouldn't be unfair to say there's still debate in the traditional empirical community about how and exactly we're going to use this hammer. And so we have a couple working groups that DOE has funded that we've put together, but I would assert there are 3 things that one would envision near term and then long term of how we would use this. First of all, just to increase our understanding of complex ground motions and interaction between ground motions and structures. I would say most certainly. You saw the last presentation, we're doing that now. I mean, these animations and simulations just give you a lot of intuition and insight into these earthquake processes. Secondly, and this is really where I would say some of the traditional probabilistic seismic hazard folks come down, is they view these tools as an augmentation to improve their probabilistic seismic hazard. They will say, you know, we cannot constrain our path effects because they're so site dependent. These types of tools will help us for a given particular site to understand how the path effects mitigate and change those waves. And so that is certainly something that I think we'll get to. And then finally, where I think the real potential is one can envision a world where we translate to fully simulation-based hazard and risk assessments and with appropriate characterization of uncertainties. You have to add that because we're always going to have uncertainties in this problem. We don't know exactly how the fault's going to rupture a priori, so we have to look at a number of fault rupture scenarios. We are never going to know the geologic structure with the fidelity that we would really like to make it a fully deterministic calculation in my view, so we're always going to have some stochastic character of that geology, which means some range of properties for that geology. So the important thing is, the final punchline is Exascale will enable us to figure out where we're going to fall on this thing, because it will give us the tools ultimately to do these types of calculations that we really need to do to have the full frequency resolution and solve these types of problems with quick turnaround and run a large number of realizations. So I am going to end with that thought. Almost out of time.
So hazard assessment helps build better resiliency. But ultimately, if you want to really save lives, you want to be able to predict when earthquakes happen. Can you, by better understanding stress buildup along the fault, get to a point where you have the ability to predict versus just understand what
You
happens
mean
when it goes.
when an earthquake will occur.
That's correct.
So I am a structural mechanics person, not a seismologist, but I have a lot of seismologists who are friends. And I think they would hold a dim view of the potential in any near term to be able to predict the occurrence of an earthquake, unless, the one-off situation where there's a sequence of 4 shocks that might be indicative of an event, something very discriminatory like that. But just wholesale prediction, I think that there is a lot of pessimism.
Your presentation was great. It was great to see the combination with Ms. Goulet's presentation. The holy grail or the target seems to be figuring out whether that getting to 15 hertz, 25 hertz, et cetera, and figuring out when that nuclear power plant is going to explode. Rather than putting a 40-story building everywhere and seeing how it might react to the hazard in that spot, we know where the power plants are. We know where the major electric facilities are. Is it possible to focus your simulations into higher frequencies but smaller spots?
Sure.
And what's going on in that area?
No, so we will do both. And we are looking at, let me say, you certainly want to understand the regional variation of risk for that structure. So we have looked for, let me just give you an example of why. So the Hayward Fault is here. Traditional probabilistic risk assessments assume all locations that are equidistant from that fault have an equal hazard. Well, you can see from these simulations that's absolutely not true. For a particular earthquake, there's a great variability. So I would say looking at those 10, 3, 4, 20-story buildings on a regional scale is absolutely important, because it will inform how we can better characterize that hazard to design those buildings. If you're in one of those buildings, like I am every day near the Hayward Fault, you would like to know that you have the best understanding you could on that. Conversely, for a nuclear power plant, and we just had a paper that went out in Earthquake Engineering Structural Dynamics, one of the values of the simulation, as I mentioned, is you would like to understand what the incident seismic waves impinging on that site look like. Traditionally, because we don't understand that, we've just assumed that all the seismic energy is essentially arriving as vertically propagating shear waves. And we know that's not true, and people have done approximations. So we just had a paper where we looked for the first time with these simulation tools, how does the plant response vary if you have realistic three-dimensional input motion versus one-dimensional vertically propagating shear wave? And so it does vary. There is a big difference. So simulation will allow you to address both of those problems, both a distributed one as well as the problem you just described of a high-value critical facility at a given location on the Earth.
You speak well to the underground simulations. How good are the structural simulations for above ground, and what's needed to improve those?
So the code that I showed you really, and Christine talked about risk-informed performance-based design. Traditional structural simulations design simulations have typically been linear elastic simulations. You've assumed that structure use a linear elastic model. And in point of fact, the essence of performance-based design is if that structure becomes damaged in some context, that may not be bad. It may be a mechanism for dissipating energy as long as it doesn't exceed a performance goal you have and fall down or become too damaged. So really, the code easy that you see on the right-hand side is a new code that is just coming online that we have developed with DOE funding between UC Berkeley, UC Davis, and Berkeley Lab to look at the inelastic response of structures so you can actually predict how that structure is damaged and yields, which is a higher level of sophistication than traditional design calculation. And so a lot of work has gone on there. And so in parallel, we're combining both of these technology sets to understand the problem.
Any other questions?
Thank you.
Thank you.